Hi, thank you all so much for joining. My name is Seth Wiesman. I'm a senior solutions architect at Verica, committer on Apache Flink, and I'm really excited to be talking to everyone today about application development, the trade-offs between microservice and monolithic architectures, how they came about, and then introduce you to stateful functions. It is looking to bring a new paradigm for building stateful applications on modern infrastructure. So I thought the best way to do this would be to start at the beginning, explain what these paradigms are and how they were developed. So initially, the world did its computing on mainframes, right? There's a single machine which handles everything. And so these things may read data from tape, do some computing, and write the results back out. Now, obviously, we've moved away from mainframe computing for a lot of reasons, but they had this really interesting quality in that they were simple to reason about. Things are more or less atomic in this model. The process either runs to completion or not. Now, of course, the world moved on to classic two-tiered architectures, or what I will broadly classify as a monolith today. Compute and storage are running as separate processes that can be deployed and updated independently, but it's still easy to reason about failure domains. Either this thing is running or not. The problem with this model is that it requires heavy coordination between teams. Everyone needs to be using the same language and library versions. We have coordinated deployments, and the system is really going to scale all or nothing. Now, recent years has seen the world migrate towards a microservice-oriented architecture, as shown in this diagram. Organizations deploy business logic via stateless tier, which allows for simple deployments, dynamic rescaling of services, and state management comes via separate tier, database, other data store. And so each of these are like their own independent entity. They have some compute and state, and then work together in some complex manner to build up our whole process or service that we expose to our customers. And this architecture has a lot of really attractive qualities, right? Teams can deploy and scale their services independently, and different components may be implemented using the most appropriate tool for the job. What has enabled this shift is what I want to refer to as modern infrastructure, comprised of four tenets. Rapid scalability of our applications and the ability to scale to zero, meaning we do not pay for idle time. Fast, zero downtime upgrades, and just generally more straightforward operations for our applications. It is now often easier to deploy another service to production than coordinate effort between teams. And so if we were to run a service that runs entirely independently or is stateless, there are a lot of really great tools we can use here. There are managed solutions like AWS Lambda or Azure Functions. There's do-it-yourself with Knative. And if we have something more complicated, we might reach for a Kubernetes service. The problem with this architecture is that things become complicated when we need to consider stateful applications or orchestrating communication amongst components. A stateful application being anything that needs to remember information beyond the scope of a single event. And so usually a request may come in and the application goes to the database. We'll retrieve some information that we use to compute a value. Perhaps we talk to another service, right? And this will do the same, talking to its data store, making some modifications. And then we respond back to the first before finally sending a final result out to the client. This is great if everything goes well, but it becomes very complicated to reason about consistency under failure in this model. If application 2 does not respond, for whatever reason, application 1 isn't going to know what happened or how it should handle that failure. Did the request or response fail? Did something go wrong in the code? Was the database updated? Is it safe to attempt a retry? Do we need to roll something back? Is everything running fine and network congestion is just causing things to move a bit slow today? All these scenarios need to be handled by application code. And so what we have here is an example of this architecture implemented on AWS. Events come in and out using Kinesis streams, and users deploy code via Lambda functions. DynamoDB will serve as our data store for managing our state. All those problems I just described are going to apply here as well. So first of all, application code has to think about consistency and retries. It will not be easy to have any sort of global guarantees about our system. If we go into a serverless context, there are a few additional problems that need to be contended with. If we were to implement communication across components like this, we are now paying for wait time. And so while Lambda function 1 calls Lambda function 2, both of these things are running and we are paying twice. Similarly for DynamoDB, there's a lot of wait time as we read from and write to the data store. And so what we might do is put some queues in between these components. And sure, now our functions are asynchronous, and only one is running at a time. And we can try and do something similar on the database side, but our architecture is getting more complicated. More components need to be monitored and paid for, and the consistency question becomes even more difficult as there are more ways things can interact with each other. Our Lambda functions are going to scale quite unlimitedly, but connections, I/O to the database, and the database itself might not. Application code will have to consider potential limits. So let's suppose that a large influx of messages comes into the system, and the number of running Lambda instances suddenly spikes up to support that load. While it may appear to be the right solution on the surface, this will cause headaches if we scale beyond the number of concurrent connections our data store can support. User code is now liable to get request-rejected exceptions that need to be dealt with appropriately. The scenario means we're now paying for wasted resources and making our user code more complex. But does it have to be this way? Well, Stateful Functions was developed specifically to solve this problem. Right? Our goal is to be a cross-platform stack for building stateful applications, making it radically simpler to develop scalable, consistent, elastic systems on modern infrastructure. And the way that we go about this is by reconsidering the fundamental problem of what component handles messaging. Why should user code call into the database at all? Instead, we want to invert the problem and have the database handle messaging for us. So this time, the incoming message goes directly to the database, and the database will call into the application. It will send a request containing the original message along with all state that is required to process this message. Application code can then respond back with any state updates to apply to the database, along with messages it wants to send to other applications or functions. And another application is invoked, right? Again, we send state to the application along with our message, and it will respond back with state updates and again, new messages to pass along. And finally, we can send a result out to the client. The critical insight here is that the database handles the messaging. And so whenever a message is lost or a connection times out, the database knows and can consistently roll back state and messaging atomically. All calls to applications are automatically made idempotent. And so user code does not need to consider retries or duplicates. From an application perspective, everything happens exactly once. Another advantage we have here is that we never need to pay for wait time as everything is automatically made asynchronous. We only invoke application code when there's something to do, and it never needs to wait for reads or writes to the data store. Last but not least, applications will never outscale their resource constraints. The database is the more difficult to scale component, but it can now apply sophisticated back pressure mechanisms to messaging as it reaches its limits. And so if we go back to our AWS example, we can see how stateful functions makes things simpler. Kinesis streams gets messages into and out of the system, and Lambda functions run user code. But this time, the stateful functions runtime will perform state and message handling consistently and correctly. Now you might be looking at this and thinking, did we really make it simpler, or did we just swap out one system for another? Well, first of all, stateful functions is solving a whole class of problem for us. Consistency and messaging are going to be correct out of the box. But we still do want to be good citizens of the cloud-native world, and that is why the runtime is also stateless. It will maintain local caches for performant reads and writes, but does not rely on being recoverable during failure. There's no need for persisted volumes, stateful sets, or other complex infrastructure components. Instead, durability comes via asynchronous state snapshots to an object store. So in this example, the durability that DynamoDB previously handled comes via S3, which is cheap, scalable, and reliable. And so what stateful functions provides is all the advantages of modern infrastructure. Rapid scalability, scale to zero, all these good things, because our compute tier is still stateless. But by combining messaging and state in stateful functions, we get consistent, durable state based on cloud-native fault tolerance. And we have robust, easy-to-use messaging primitives between all these components. All communication is going to occur through message passing, and functions can message each other based on logical addresses, even with strong ordering guarantees. There is no need for service discovery or queues within our system. And this whole thing is implemented on top of the Apache Flink runtime, which has been proven out at scale in production for many years. So we're able to leverage its distributed coordination, ability to handle multi-terabyte state, and highly optimized networking stack. So with all this in mind, let's dive into some of the concepts, right? What does it look like to actually build something with this thing? So typically you will develop your application by implementing several services, or what we creatively call stateful functions, that are basically small bits of code or logic representing entities within our application. So we could, for example, write stateful and application logic in any language. The project does ship with Python, Java, Golang, and TypeScript SDKs, but you can use any programming language you like by implementing our well-defined protocol. And because the runtime is language agnostic, functions can communicate seamlessly cross-language without any ceremony. As previously mentioned, all communication does occur through message passing, and function invocation only occurs when there is actually a message to process. This means our functions are not consuming resources unless actively engaged. So the runtime in the background will set appropriate context, such as state and other metadata for each message, allowing us to model our entities in a very fine-grained manner without exploding our hardware resource requirements. So we can, for example, define a stateful function representing a customer with a single logical entity modeling every single customer within our system. The number of logical entities may then grow indefinitely as we sign up new customers, while the number of physical instances only needs to grow or shrink based on active throughput requirements. Next is dynamic messaging with consistent state management. This means we are not predefining communication patterns here. Any function can message any other arbitrarily by sending a message to its logical address. And by working with logical addresses, we both avoid service discovery, we don't care where any given service is running, and have easy cross-language compatibility. So I can have a Java function that invokes another Java function, but it could also invoke a Python function and it will look exactly the same. And we're able to do all of this with what we call exactly once state semantics. So functions have access to address scope state, where they can store durable variables that will be persisted across invocations. The runtime will then integrate messaging and state updates for out-of-the-box efficient consistency across event inputs, application states, and outputs delivered from the application. So this is our first look at a little bit of stateful code. It is a greeter. It's sort of our hello world example with a twist. And that twist is that when we say hello to a user, we're going to customize that greeting based on how many times we've seen that particular user so far. First thing to notice is that this really is just plain old Python code. We are importing the stateful Python SDK, but for the most part, this should look like any other code you've ever written. We've defined this greet function with two parameters, a context, which gives us access to our runtime capabilities such as state and messaging, and then the actual message that was sent to this function. This decorator is how we bind this physical function to the runtime. And all these functions are associated with a logical type name. So this is the logical name by which we can send messages. Someone that wants to invoke our greeter does not need to know that this is Python code or where it's running. It simply sends a message to the type name com_example_fun/greeter. Now this type name, defines the sort of function under invocation, right? So it says this is a greeter, but we always send messages to an address, where an address is a particular instance. Think of it as sort of an ID or like a row in a table, right? What specific row are we interested in? And all of our state will always be scoped to that particular instance. So in this example, our ID is our user ID. So we're able to keep track of things independently for every single user of our system. If we go into the heart of this function, we can see what it looks like. And this should look like very simple Python code you've seen a million times in the past. So we have our message. Messages are always well typed, and so we can extract the actual variable from this. In this case, we're treating our message as a string and saying this is our user's name. And then we have access to this address scope storage where we can maintain variables, such as scene count in this example. We're tracking the number of times we've seen this particular user so far. But we can treat it like any other variable, right? We can read it, we can write it, we can modify it, whatever we want to do. And finally, we'll send a result out. So we're going to send a greeting to a user's mailbox. We're saying, hey, send it to the mailbox function type. Which particular one? Well, the one for this user's name. And the way that the runtime will interact with user code will allow us to seamlessly take advantage of these modern deployment tools like AWS Lambda or Kubernetes services, retaining their operational management benefits. When a message targets an address, it is first going to be routed to the database shard, storing its state within the runtime. Only then is the message and its state value sent to user code as a single atomic payload. The response will then contain the new messages to send to other functions along with any state updates. Because this protocol encodes all information in a single payload, the invocation is trivially idempotent, allowing for simple retries. And then the runtime will handle all the asynchrony for us, invoking multiple independent functions at once for scalability, while knowing which ones require strict ordering to remain consistent. We have here a model where compute and state are logically co-located for consistency, but at the same time physically separated. We can deploy independently and scale different components when using any language on Stateful, giving us the operational benefits of a microservice with the consistency of a monolithic architecture. Now, Stateful is not going to have any opinion on how user code is written or deployed. Instead, each SDK will come with what we call a request reply handler. And this is the thing that actually implements the protocol on the SDK side, but it does so in a framework agnostic way. It does not perform any network I/O and is embedded easily into your deployment framework of choice. So for example, we might use the Python SDK to deploy our function using AWS Lambda, but could also deploy it using a standard web framework like AIO HTTP or Flask. Alternatively, we could use the Java SDK and a web framework like Undertow or even Spring Boot. The Golang SDK simply implements the standard Go HTTP handler interface, so it can be easily embedded into any standard Go framework. And again, all these SDKs use a standardized type system, so functions written in different languages can communicate together seamlessly. Now, with all of this in mind, right, what can we actually do with stateful functions? Well, one strong use case is model serving. And the last decade has seen companies heavily invest in machine learning. Teams of data scientists can now build models that solve these complex problems that were out of reach just years ago. But unfortunately, that's only one part of the problem. The real value in machine learning comes when successfully deploying models to production. But according to industry reports, only 22% of organizations using machine learning have successfully deployed at least one model to production. And out of that cohort, over half believe deploying another would take at least 90 days. Why is this so difficult? What requirements do we need for a proper model serving infrastructure? Well, first of all, we need to continuously deploy the actual model without downtime, as the team refines it over time. So this deployment needs to be rapidly scalable, right? Models might require expensive hardware, and so it's crucial we can rescale with traffic, never paying for unused resources. But beyond the model itself, we have all the components sitting around it. Data points need to be processed, cleaned, and stored for future vectors. Users may have different configurations specifying how the system should interpret model scores, and of course, a component to actually act on that model's output. Teams other than data science may be developing these components using their own programming language and libraries of choice and be on an independent deployment schedule. These are exactly the types of problems that Stateful Functions was designed to solve. And in fact, I am so confident we can solve them, I'm thrilled to announce we have successfully funded our next startup, Fraud Alert Inc. And we are coming on board to bootstrap our ML ops team. So we're going to take this highly sophisticated model our data scientists have developed and get it into production. Our company will process credit card transactions and alert customers if we believe a transaction to be fraudulent. So this diagram shows a high-level overview of the application. There's a transaction manager or coordinator that is going to build up this feature vector across several different dimensions before sending it off to the model for scoring. If the model were to respond with a value above some threshold, we'll go ahead and say, hey, we think this is fraud, and send an alert to our customer. All of this is going to be done with consistent state, independent deployments, and support for rapid scalability. So I've gone ahead and actually implemented this system, and we're going to take a look at just a couple of what I think are the interesting components. First thing to look at is our transaction coordinator. So when a transaction comes in, it is first sent here. And this is going to build up that feature vector for us. So I'm using the Java SDK, and this is running as part of a Spring Boot application. So I have a couple value specs. These define the things in our address scope storage that are persisted. And so we're going to store the transaction and the things that we build up as part of our feature vector. And so If a message comes in that is a transaction, because we can plug in our own types, we'll go ahead and store that into our storage so that it's available across invocations, and then send off messages to these various functions. We have a counter function that keeps track of how many times a user has reported fraud for this particular account over the last 30 days. And we have a function that is going to give us a trustworthiness score for a given merchant. When these things respond, we will build up our feature vectors before finally sending them to the model. And then the model will finally report back to us some score, and if it is above some given threshold, we'll go ahead and send an alert to a Kafka topic with all the information we need to alert our user. So we can go into the fraud counter, and this is running in the same Spring Boot application. And it has one persistent variable, a counter, that is an integer. And so if a fraud confirmation comes in, says, hey, users reported fraud for this account, we will go ahead and increment this counter. And then we're actually going to send ourselves a message for 30 days in the future to expire that count. So we get a rolling 30-day count. And now we can check if our message was a string to query the value. Then we will simply get our count out of storage and send it back to the caller. We'll send a message back to the transaction coordinator. And finally, if it was a string and it was to expire, meaning the message we sent 30 days ago up here, we'll go ahead and decrement that count, eventually going back to 0 and deleting it entirely. Now, for our merchant score, we're actually talking to a third-party API that is going to give us that score, right? We're using some other service. And well, Golang has really great HTTP handlers, and I thought, why don't we implement this function in Golang? So we have the merchant score, and it's going to try and look Golang idiomatic, but all the same concepts will still be here. So I have our value spec. I'm defining some variable I want to have in my address scope storage. We'll call it our score, and it is an integer. And it is going to automatically expire 1 hour after it's written. So we're using our state as a way of having a perfect cache. As a message comes in, if it was to query, right, that message we sent from our Java transaction coordinator, then we'll go ahead and check and say, is there a score in storage, right? Is there something in here? If not, we'll go hit the actual third-party client, take that result, and write it into state. Finally, we'll send our score back to the transaction coordinator. This way, we're not making too many calls against our REST API. We're being good citizens there. And we have this perfect cache because after an hour, it'll automatically be deleted, and then we'll make another call because that score might change over time. Finally, we can look at our model, which is going to be written in Python because that is where most people do their data science. A message comes in that is a feature vector containing those different points that we built up. And then we have our highly sophisticated model, in this case, a random number generator. But this could be TensorFlow or NumPy or any sort of Python machine learning library you so choose, because this is real Python code. And so we'll get that score and similarly send it back to the transaction coordinator where it is received down here, and we can act on that result. I have this thing up and running, and we can see some things that it is doing. There's a lot of logging going on here, but you can see there are transactions coming in. We are getting merchant scores. We are sending things to different functions. And finally, we are sending out alerts when something occurs. So that is a whirlwind tour of stateful functions, right? Our goal is to make it radically simpler to build stateful, consistent applications on modern infrastructure. I hope you enjoyed this talk, and if you would like to get involved, please feel free to reach out either on our mailing list or at statefun_io on Twitter. Thank you so much.